Good day and welcome back to what I guess is technically the fifth part of our discussion on differentiating exponential functions, but really in this video we are going to focus in on properties of logarithmic functions. In our textbook, 6.3 is a very short section focused on some of the basic properties of logarithms so that we can eventually get to differentiating these logarithmic functions. And because it's a short and quick section, I would just usually group it together with the 6.2 material on a second day of discussion in class. And with that in mind, let's go ahead and focus in on the logarithmic functions. The logarithmic functions are simply defined to be the inverse of the exponential functions. So a bit more specifically here, when a is not equal to 1, we can think of the graph of this exponential function a to the x. It's either strictly decreasing or strictly increasing, depending upon the value of a. In either case, it's 1 to 1. It has an inverse. The inverse of the exponential is the log function, and denoted by log base a. So how we define it then is log base a of x is equal to y if it undoes the exponential function. So when a to the y is equal to x. And this is why you may hear people refer to a logarithm as being an exponent. This y that we get out is the exponent of the base a that gives us back that input, x. So let's think about this graphically. And I'll draw the picture of the case when a is larger than 1, just for convenience. The graph of y equals a to the x is an increasing exponential function. It has y-intercept of 1, so there's 0.0, 1. To get the graph of its inverse, which is the log function base a, we reflect this graph of y equals a to the x about the line y equals x. And when you reflect it, you get back this curve. So note if 0, 1 is on the black curve a to the x, 1, 0 would be on its reflection about the line y equals x. And this is the graph of log base a of x. So in terms of some basic properties, so remember the logarithm base a is the inverse of the exponential function a to the x. So the log base a of a to the x should undo that exponential, and you simply get back x. And this is true for any possible x. Similarly, a raised to the power of log base a of x. Remember, log base a of x undoes the exponential. So what we would get back is x, and here we have to put a small restriction. It's as long as this logarithm makes sense. And note, the domain of the logarithm would only be for positive values of x. And this is an observation that we should probably note in our graph to the right. The domain of the log base a function is going to be positive values, and its range is going to be any possible real number. So the range of log base a of x, all of those possible outputs, is all possible numbers. And then similarly, we can see a limit of interest. The limit as x approaches 0 from the right of log base a of x. So an input close to 0 on the right, our graph is approaching minus infinity. And then for completeness here, let's also note that as we approach infinity, log base a of x also approaches infinity. Now on to the more common algebraic properties of logarithms. And before I write down these properties, I would encourage you to pause the video, give yourself, I don't know, maybe say a minute, 90 seconds, and fill in these three properties. So for the first property, the logarithm of a product is the sum of the logs. So this would be log base a of x plus log base a of y. The logarithm of a quotient becomes a difference of logs. That is, it's log base a of x, that quantity in the numerator, and we subtract away log base a of y, the quantity in the denominator. And finally, if you have an exponent inside a logarithm, that becomes a constant in front. We can write this as r times log base a of x. And we will make frequent use of these common properties of the logarithm. In fact, the logarithm that we work with the most frequently is log base e, and because it is something that we encounter frequently, we give it a name. We refer to this as the natural logarithm. And let's make a couple quick observations about this natural logarithm. And the first two bullets are really just restating our initial two bullets. The natural log undoes the exponential function. So we should get back x. And e to the natural log of x should also give you back x. But note there is a restriction here. We need a positive input for a logarithm function. Its domain is 0 to infinity. And finally, natural log of e is really natural log of e raised to the first power. And what we would get back is simply that 1. When it comes to working with logarithmic functions, the natural logarithm is the most convenient. That is to say, e is the most convenient possible base. And there is a change of base formula that allows us to rewrite a logarithm base anything in terms of the natural log. And I want to point out why this is so convenient. Natural log of a, this quantity we are dividing by, is a number. So this is really equal to 1 over natural log of a times the natural log of x, where 1 over the natural log of a is a constant. And what this is indicating is if we know how to, say, differentiate, or later on in this course, integrate the natural log, we could extend that to differentiating and hence integrating log base anything using this change of base formula. Hopefully this provides an overview of the basic properties and definition of the logarithmic function, and I also hope that most of it was reminders in the sense that it seems somewhat familiar to things that we've seen in the past. In our next section, we will utilize many of these properties to differentiate the logarithmic functions. But for now, we are in this perfect position to work some more examples. If we were meeting in person, this is when I would have a class worksheet and I would turn the floor over to you. And typically what we would do in class is I would have you turn your desk, work with your neighbors. I'd give you probably 20 minutes to invest into this worksheet. And I purposely put more examples, more problems on the worksheet than I think we can get through in class, with the idea that it will provide you with additional practice problems. Then to help you out, I post my full typeset solutions on Canvas so you can continue working these examples and then check your work versus the solutions that you see on Canvas. And it also shows you kind of the notation and the presentation that I'm looking for in your work as well. Now, we can't model this exactly in this more remote setting, but what I can do is suggest that before going to the next video, log into Canvas, find the associated class worksheet for differentiating exponential functions, and give yourself a solid 25 or 30 minutes to work through these examples. In the next video, we will recap just 2 or 3 of the examples on the worksheet, and I will leave the remaining ones for you to think about and compare your work with the full solutions on Canvas. So stay tuned and take care.